My name is Eduardo Gonçalves and I will be presenting my thesis work. It will include the update of a low-temperature plasma simulation tool named LoKI, which is part of the Kinetic Testbed for Plasma Environmental and Biological Applications Kit Plasma-B, an ongoing research project. This work is targeted to low-temperature plasma. So first, let's see how do we get to this kind of plasmas. Let's start at a very low temperature with nitrogen in a solid state. If you keep increasing the temperature up to a melting point, it will become liquid. Now, if you increase up to a boiling temperature, nitrogen will pass on to a gas state. What if we keep increasing the temperature? Well, we will start to have some new interesting particles. Molecules will now have so much energy that some of them can no longer hold their electrons, and as such, they will ionize, producing electrons and ions. Let's study this system in a greater detail. So you have mostly molecular nitrogen, a bit of electrons, and a bit of positive ions. If we apply an electric field, we will give energy mostly to electrons. An energetic electron may collide with a neutral particle producing an ion and other two electrons. Or we can have an electron recombining with an ion producing a neutral particle and a photon. So these reactions will happen throughout the gas producing light and electrons. This is called a gas discharge, and this is the form of low temperature plasmas that will be studied here. One of the most important conditions for this system is the Schottky condition. This condition tells that the number of electrons lost in the system must be equal to the number of electrons being created in the system. However, the use of low temperature plasmas for technological purposes, such as plasma jets for enhanced wound healing, demands a fine-tuning of its parameters. In order to find out these parameters, we need simulation tools, and for this we use LoKI. LoKI stands for Lisbon Kinetics and is a computational tool that simulates low temperature plasmas. It is essentially composed by two modules, the Boltzmann solver and the chemistry solver, that will work in a self-consistent way to find the end results. In the chemistry solver, the possible reactions such as ionization, combination, attachment, charge transfer, and others are accounted for. Since many of these reactions are triggered by electrons, it has a Boltzmann solver. This module solves the electron-Boltzmann equation, accounting for electron collisional reactions, and as a solution it has the electron energy distribution function, or EEDF. This is a probabilistic function that tells the expected number of electrons for a given energy. With this function, it is then possible to calculate rate coefficients and other quantities to be used on the chemistry solver. So by now we have encountered ionization many times. It is important to test the Schottky condition, to calculate the electron energy distribution function, and to calculate rate coefficients for the chemistry module. One of the most important types of ionization is the electron-impact ionization. This is a process in which a high-energy electron collides with a neutral particle, producing two electrons and a new ion. My work will be to program an ionization routine in the Boltzmann solver. This will improve current predictions of the electron energy distribution function, leading to more accurate information to be used on the chemical model. This will not only improve the Boltzmann solver, but also the chemistry solver, and as a result it will improve LoKI simulation tool as a whole. Thank you.